Okay, welcome to video 18. We're jumping into inner product spaces, which we know a little bit about already, but now we're just going to make it formal. And one of the reasons I love this book so much is because it comes from starting in Rn and then building to standard vector spaces, where other books start with standard vector spaces, which seem really abstract. And then their main example is always Rn. And I like this direction better. So this will look familiar, but now we're going to generalize this idea to general vector spaces. So we start by letting V be a vector space. Okay, an inner product is a function that maps V to R. And the function is defined to be angle, comma, angle. And there's a reason why in Calc 3 and other classes I don't like it when people use this for a vector. This is I plus 2j plus 3k. I don't like this notation because we use these bars, these angles, for this function. Okay, and so that's why I've never been a big fan of that, because it's easy to get confused. They're not the same thing, right? And so this is how I like to write this. It's kind of cool. The book doesn't do it this way, but the function angle, comma, angle takes V and maps it to R. And this thing has 4 axioms that must hold true for this to be an inner product. So 1, if you take 2 vectors in V and you take their inner product, it has to be the same if you switch them. 2, if you take the sum of 2 vectors, inner product with another vector, this needs to equal this. So inner product distributes across addition. That should be, I'm trying to be careful here. Plus VW. Okay. 3, if you take a vector and multiply it by a scalar u in the first position, this equals C times uv times the inner product of u and v. And then 4, the inner product of a vector with itself has to be non-negative, unless if u equals the 0 vector, then the inner product is 0. All right, so let's look at some examples here. And sure enough, the first one, let V be Rn, and let the inner product just equal dot product, as we know it. So in other words, this is equal to u dot v, which is equal to u1 v1 plus un vn. All right, so this defines an inner product on Rn. This will be example 1. And we're going to build from that. We're going to make our own. Well, we're going to see if we can't make our own inner product and test these 4 axioms. So we're going to work on R2. So we're going to let V equal R2 and let U and V be vectors in R2. We're going to define the inner product of U and V this way. By this equation. Should make that red. Okay. So this equation 1 is the definition of our inner product. So it's almost like the standard dot product, but it's got a tweak. And now I want to verify that this defines, or show that this defines an inner product. So one, we want to show that UV equals VU. That's called symmetry. Okay. Go back to black here. Right. So now we do a computation. So the U inner product V is 4 U1 V1 plus 5 U2 V2, and this is an R, so this is 4 V1 U1 plus 5 V2 U. So I guess we put here properties of R. 4 V1 U1 plus 5, and that equals VU. So check. Okay, 2. This is the hard one. This is the hard one. You want to show that U plus V inner producted with W is UW plus VW. Okay, we can do that. So start on the left here. U plus V W equals, what does it equal? It takes 4 U1 plus V1 W1 plus 5 U2 plus V2 W2. All right. Now we're working in the real numbers, so you can do anything you want willy-nilly. This becomes 4 U1 W1 plus 4 V1 W1 plus 5 U2 W2 plus 5 V2 W2. Rearrange these. 4 U1 W1 plus 5 U2 W2, taking 1 and 3 here, plus 4 V1 W1 plus 5 V2 W2. Now, just so it's clear, this is UW, and this is VW. Okay. So that guy checks out. Check. 3. Show that CU comma V equals CUV. Okay. All right. So let's let C be some constant. So now we have CU comma V, which is equal to 4C u1 v1 plus 5c u2 v2. And again, we're working in the real numbers. So we'll bring the c out front here for u1 v1 plus c 5 u2 v2 factor. And sure enough, this equals c times the inner product. Check. Okay. And lastly, number 4. Show that u with itself is greater than or equal to 0. All right, so we assume u is not the 0 vector. If it is, you just get 0 plus 0 equals 0. So, all right, so u dotted with u is 4u1 plus 5 u2 which is 4u1 squared plus 5u2 squared, which is non-negative because these are real numbers, and 4, 5, u1 squared and u2 squared are all greater than or equal to 0. So check. And now this thing that we defined is an inner product. It's very tedious, but I still have memories of doing this. Okay, so now we've done the example with R2. And well, this is the part where it gets super fun because we're going to extend this to something not Rn-ish. Okay, so I'll make a note here. In Rn, particular, R2, the idea of length is sort of easy to understand, because if you're in R2, say, and you're given some vector, 2, 2, right? And what's the length of that? This is 2, that's 2, and this is, what, root 8? Yeah, 4 plus 4 is 8. And you actually can get a measuring stick and measure that, right, whatever the units are. But now, so the length of this vector v is root 8, right? But now this idea of length, how do you measure the length of so let's say, because we're about to work in the polynomial space in Pn. How do you measure the length of a polynomial? Well, it depends on the inner product. And the inner product gives us a length, because if you think about this, we just showed that u dot v was u1 v1 plus u2 v2. This is an R2, and it's really well, if you look at the length, how can I say this? Let me erase that. It's not coming out right, Pullman. If you look at the length of the vector v in R2, I mean, what is it? It's v1 plus v2, which is v1 squared plus v2 squared, right? But it's square rooted, right? And so the length of v is the square root of the inner product. Or better yet, the length squared is the inner product. So it depends on what the definition of the inner product is. And you can see I'm struggling because we always want to think in terms of vectors. We've been hammering that with you forever. So let's just keep this in mind as we go through this next part, because it's very abstract, but not. Okay. Okay. We're going to define, so example 3. We're going to define an inner product on Pn as such. If you let P and Q be polynomials in Pn, and let T naught down to Tn be real numbers, inputs, define the inner product of P and Q by this cool evaluation. You go P of T naught times Q of T naught plus P of T1 times Q of T1 plus dot 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 P of Tn times Q of Tn. I'm not going to go through the gruesome details of this because I have something better to show you. I might actually assign that as homework, but this does define an inner product on Pn. You show the 4 axioms. It takes a little time, just like all that did for me. But if you take your time and use this function properly, it pops right out. All right. Well, now that we have Gram-Schmidt, we can use Gram-Schmidt to produce orthogonal bases for any V. Before, when we did the Gram-Schmidt process, the function we used was dot product, and now we're just going to use inner product, which is the dot product on Rn. Okay. All right. So this is going to take a while, but we got time, and we're gonna do something pretty cool here. So let V equal P4, and we're gonna use the inner product defined above, which by the way is called evaluation at T naught down to Tn. All right, so here we go. For this example, we're going to let T naught equal -2, T1 equals -1, T2 equal 0, T3 equals 1, and T4 equals 2. So evaluation at the numbers -2, -1, 0, 1, and 2. Okay, and now we're going to show that W equaling P2 shows up as a subspace of P4. And remember, P2 has dimension 3. Okay? And we want to produce an orthogonal basis for this W, which is isometric or isomorphic to P2. Okay. So what we need is a basis for P2, and the standard basis is 1t comma t squared, right? All right, and so I did this, and I used it's standard to use polynomials P1, P2, and P3, but there are so many different indices floating around that I use P, Q, and R as the vector polynomials. Okay, so what we're doing now is we're now taking these three vectors in P2. I'm just trying to get used to calling them vectors, and we're going to make them orthogonal. Okay. All right, so let's use Gram-Schmidt here. So if you take the first polynomial P, which is equal to 1, and you evaluate using the inner product, you get the vector 1, 1, 1, 1, 1. If you use the vector Q of t, which is t, and you evaluate, you get minus 2, minus 1, 0, 1, and 2. And if you choose the third vector here, r sub t, which is t squared, and you evaluate, what do you get? You get 4, 1, 0, 1, 4, right? So now we're looking at vectors in R5 that are representing these vectors in P2. All right. So the question is P dotted, or sorry, is P inner product Q is that equal to 0? If it is, then those two vectors are orthogonal under this inner product. So let's do this now. P dot Q is going to be P of minus 2, Q of minus 2, plus P of minus 1, Q of minus 1, plus P of 0, Q of 0, plus P of 1, Q of 1, plus P of 2, Q of 2. Let's see. So this is 1 times negative 2 plus, where the hell am I? Oh, 1 times minus 1 plus 1 times 0 plus 1 times 1 plus 1 times 2, and that is minus 2 minus 3, 0. So we already have two orthogonal basis vectors here, P and Q. And now we want to produce, well, let's see, let's check, is one perpendicular to R, is P perpendicular to R, or orthogonal? 4, 5, 6, no, it's 10, nope. So check it out, P dot, see, P inner product R is 4 plus 1 plus 0 plus 1 plus 4, and that equals 10. So not orthogonal. All right, but P and Q are, let's see, is Q orthogonal to R? Doesn't matter, but we're going to check anyways. Minus 8 minus 1 plus 1 plus 8, and that's 0. Yeah. So we're close. Anyways, let's run Gram-Schmidt on this thing and see if we can't make R perpendicular to both P and Q. So going back in our notes to Gram-Schmidt, so this is notes bit. If you have a book, look at it, but this is how you found a third vector. It turned out to be x3 minus writing all these arrows out. And these two fractions here are filled with dot products. Well, we're not working in R anymore. Okay, so our new V3 is going to be x3, which is t squared, minus the inner product of t squared and 1 over the norm of 1 times the vector polynomial 1 minus t squared inner product t over inner product t and t times t. Okay. So t squared 1 we did before, that's 10. 1 with itself is 5 times 1 minus, so t squared t gave us, we did that before, 0, because they're orthogonal, so it doesn't matter. T squared minus a half, no. 10 divided by 5 is 2. Okay, so here's our polynomials. P equals 1, Q equals T, and R is equal to T squared minus 2. These are orthogonal bases. For P2 under this defined inner product, which we're calling evaluation. Okay. And if you're not clear on that, let's go back to R5. We showed this first vector was 1, 1, 1, 1, 1. The second vector t was, that's just identifying, minus 2 minus 1, 0, 1, 2. And let's get this third one here. So if you plug in minus 2, that gives you 2. If you plug in minus 1, you get minus 1. If you plug in 0, you get minus 2. If you plug in 1, you get minus 1. And if you plug in 2, you get 2. And if you look at them this way, you see that all of these are perpendicular to each other. Orthogonal, apologies. Right, so minus 4, minus 3, 0, minus 3. Yeah, all works. Okay, added to homework 8. This is section 6.7. Problems 4, 6, 10, and 14. After yesterday's conversation, I decided to no longer, just going to grade on completion. See that you attempted it. If you want feedback on the level I've been giving, you have to ask for it, so request it. Homework is now worth less. And the final is going to be an oral exam, 30 minutes long. I can get I think half of them during the day of the finals on the actual final time, and then the other half will be other times. So keep that in mind. And I can't make you do any kind of work on breaks, but if you wanted to, you could take it on Thanksgiving or or Black Friday. That whole weekend, if you wanted to get it done, or wait until finals week and then we'll figure out a schedule then. And yeah, like I said, if you have any questions on these homework, I mean, don't beat your head on a wall for 3 hours, and just email me, and or come to office hours, or ask to have a Zoom chat. Last week I made videos, these little short ones, just because it's so easy for me to do that, and just post it on YouTube on how to start or mostly finish these problems. Cool. All right, I don't know how long it took. It took a long time, but yeah, this is good stuff. See you in a bit.